Hello, everyone. I could speak Spanish and Italian, but I prefer to do the talk in English. And I just want to thank the organizers for inviting me here. It is always a pleasure for me to come to Argentina. Also because just about a third or more have Italian last name. I was just talking to a journalist and he asked me, what do you think of what happens in Argentina? And I said, Argentina has some of the best agricultural scientists in the world, and I mean it. So I have one right in front of me, my friend Ricardo. So it's a privilege to be able to share with you the results of what I have been doing in my lab, and I've stolen one of Ricardo's members in the lab, Susanna, that is performing her PhD, finishing her PhD at Michigan State. So it's always nice to be able to talk for an hour, maybe a little less, because it really allows me to give you an overview of the different angles of digital agriculture. And let me see. Okay, so I'll go quick on some on the introductions, but you know that agriculture is going through a digital revolution in any sense, even though sometimes it's correct, sometimes it's not. People think that the future may be just in sensing, sometimes robotics, and the possibility of now be able to spray with drones or applying water to every single plant. And the problem is that sometimes the technology is sold as a complete solution, but it's just one piece of the issue. And so that is very important, that the enterprises oversell the technology thinking that they're going to solve the problem, and often the farmers do not find that to be the case. Just briefly, you all know this, but there is a very specific reason why I'm showing this. In beginning of the past centuries, we had the possibility of using greater machinery, and that allowed us to have a much extensive level of cultivation, increasing yields. At the same time, these were the first serious environmental impact, because there was the greatest environmental impact, the Dust Bowl, when all the plains in the US were tilled, but the soil was not covered with residues or other plants. So now that we had much bigger areas, we created the first environmental problem of soil erosion. After that, because you had a bigger areas and the plants needed to be able to have nutrients, then the agrochemicals allowed us to basically boost yield. That was the second environmental problem, which was starting to pollute water qualities and leaching. And then we had biotechnology, a really game changer, but that did not come with a price, because many countries still do not allow to cultivate genetically modified organisms, which is still a limitation for them. It's just crazy. But in the last few years, we have data science, right, as basically the breakthroughs, and you see all the different technologies, robots, satellite, big data, drones, sensors. But in the next few years going forward, things are moving into, it's a term that in engineering is pretty often used, the digital twin, so gemello, right, as a proper definition. So digital twins for proper agriculture is the bridge between the physical and the digital world to promote innovation and performance. And if you read that definition, it's not just a virtual model of everything, of a process, of a product, of a service. That's very much used in the car industry, in anything that deals with man-made system. You have a digital twin. before you reproduce, you basically have the design on the computer, where we can design plants on the computer now, both from a genetic point of view, as well as by linking synthetic biology with sensing and system approach. And so that's why I think you'll see how digital twin is used in the work that I do. Another critical piece that is happening is the US has now really invested a lot in the concept called One Health, una salud, la salud del medio ambiente, so healthy ecosystems, healthy foods, healthy farmers, and healthy communities. So now most of the projects are presented with all the pieces of the technology integrated. And so right at the middle, you cannot have healthy foods unless you manage your resources, unless you manage your soil well, unless you manage, you know, the environment and so on. So the problem, healthy farmers, is also from an economic standpoint. Between the pandemics and fluctuations in prices or lots of other, you know, policy changes, farmers are the ones that they really face a lot of the risk. And there has been quite a bit of, you know, very sad situation of farmers being sold and the health of the farmers not being in the most suitable situation. And so then the healthy communities is what you'll see more towards the talk about, you know, carbon markets and food companies. But healthy communities are the consumers which demand better food, better healthy foods, but not often willing to pay for it. And so it's interesting that everybody puts pressure from different angles, but then in the end, it all falls down to agriculture, and agriculture falls down to the farmers. So we got to break that. So anyway, regenerative agriculture is this term. I haven't heard much of it, but it's basically an integration of everything that we always studied. You know, conservation agriculture, but digital agriculture plays a critical role in regenerative. And so the principles are just the principle of agronomy, basically. You have high diversity, you got to change. We can't just keep growing corn after corn and after corn. So here at least you do a little bit of rotations, corn, soybeans, and that's okay. But the third and fourth crops are critical, not just from healthy sorts of, you know, diversity in the food system, but because the microbial diversity, the microbes in the soils, we have found that at the long-term ecological sites, at the Kellogg Biological Station, that when you change the very intensive rotational system, has a diversity of microbes that sequester much more carbon, even though the carbon input is lower. Even if the plants are lower, the microbes are able to cycling, and because of the aggregate stability, they are not broken, and carbon is kept inside, and so rotations is a critical piece. Circularity is something else that I will describe, and it deals with recycling this, you know, basically the nutrients. The problem in agriculture is that agriculture is a leaky system. It's like a colander when you drain your pasta. You can't just stop. It will always happen. And so how can we be more circular? It's by using in more efficient use of the resources. So you only put, and that's again a connection with the digital leg, you only put the right amount where is needed and not where is not needed. And that's obvious, but it's difficult to do. There is a push to integrate animals, you know, in the system, be able to graze forage, and be able to link digital technologies to improve pasture management, nutritional value of the grasses and so on. And then push it for, you know, cover crops, perennials, agroforestry. You'll hear more about the way I define precision conservation by removing constantly low productive areas. And then obviously continuous steel and precision technology. And the advantages are pretty clear. Reduction of greenhouse gas emissions, increased soil carbon sequestration, biodiversity, pollinators and habitat. People don't realize that 35% of the food that we eat depends on insects and pollinators, and the biodiversity is going significantly down. Okay, so profitability is important. One of the reasons I can share a lot of the data is, what we found is we have an extensive amount of data sets across the US, and it's actually becoming even much greater with the possibility of having some of the data shared by the seed companies. But anyway, so those are just to give you an overview of how, the amount of yield maps, as you'll see, changing the conversion into yield stability. You hear more about that. We have thermal imagery. I was pleased to see the previous work presented by Marcos about getting, thermal to understand soil-water balance and managing as well as not just water, but nutrients as well. So we have thermal stability map for very large areas. So this is an example of the fields blown up, of what we have, right? You have, I also described earlier to someone I was talking to that farmers often forget about temporal variability, which is a critical piece. If you were to make a variable rate map based only on last year's, you will miss a significant amount of behavior. So if you look at this field, it's never, the yield map is never the same. At the same time, variability is not only dependent by soil, because if it was only soil driven, the yield maps will look alike every year because the soil doesn't change. So it's interaction between position in the landscape and climate, soils, as well as if management is done correctly. And so you're familiar with some of these concepts. One other way of showing the zones, the management zones, is through a yield stability. So by looking at how each single pixel is different from the neighbor and how is it different over time, you have areas that they constantly produce high over time. So this is an example, this particular field, I could pick any of this, as you'll see, out of 80 million acres that we map. It's for 12 years. And so high and stable, low and stable, constantly underperforming, and medium and stable, it's more in the middle. But then you have the one that they are unstable, which they fluctuate from one year to the next. Now, if you look at this map from the same field, we have been flying for several years over, and you have the same concept is converted into now what is called cold and stable. So, as you know, if plants have evapotranspiration, they're cooler. That's the way they defend. And so the areas that they're cold have more water available. So that's how we parameterize the crop model for soil depth, to be able to know how much water is stored as a soil depth. So cold and stable is pretty much a mirror image of the high and stable. And all the others, low and stable, the hot and stable, that means the bucket, the soil is much shallow. And so they run out of water and the plants get hotter. And so they have higher temperature. So we fly this over thousands, close to millions of acres with a combination of collaboration with airborne imagery. And so combining yield stability map with thermal stability map and optical of the most commonly used, even though we run several indices, and this is a way to start separating some of the factors. Which area is driven by water, which area is driven by basically sizes, potentially skips in areas that they're missing. So this is pretty impressive for us to see in the fields how much nitrogen, obviously, needs to be managed by matching water supply. And so that's a critical piece of thermal stability map. Not sure. It'd be easier to have set block. Anyway, so far this is a good time. Do you everything is clear so far with the English? We're gonna leave time for discussion, which can be in Spanish, and so I want to make sure that you capture. I'm trying to speak slow and trying to make the message clear. So Let's see if I can go fast. Keep going, yep. Next, next. Una más. So I can give the presentation without the maps. So what we did after understanding with the data that the farmers had shared with us, we expanded the work using satellite imagery. And so the satellite imagery across the entire corn and soybean belt of the US. So we looked at the changes in reflectance between the high and low, and the same exact concept. And we've been basically developing yield stability map for 80 million acres, for 40 million hectares of corn and soybeans. And so now anyone can basically go to a website and be able to click on the field and get the information about the yield stability. So that's basically the slide that was coming there. The yield stability after, it's the basis to deliver prescriptions. So prescription maps, because it captures the history of the site. Okay, you understand which areas are low, which areas are higher yielding. Then we link the remotely sensed images with crop simulation models to identify what are the best rates to apply. And so that will be the basically one piece of the technology that I will present. The other two aspects that I will describe are precision conservation, how we identify areas that could have alternative land use, and how the soil carbon markets. I asked Ricardo and other colleagues that's something that in the US is becoming more popular. Here, I heard you just starting to talk about, but it's a pretty complex subject because the quantification of soil carbon is really difficult. And so it's both the three aspects, the biodiversity, precision conservation, the variable rate application across not just one field, but again, how we distribute them across these 40 million hectares, and how the technology is integrated to have a certification scheme that the farmers could basically use to show how much reduction. There we go. So we used this slide actually has got a few years old, but when we published the paper, we had 10 years of yield data. So you can click now on any single field of the US. So you can test it. The site is available and it's free. Farmers can look at it. You'll have explanation more at the end of the talk. What the striking results is the consistency of the numbers. So 48% of the fields within field, so almost 50%, always high yielding. But then you have 25% is always low yielding. When I say low yielding, it doesn't mean no productivity. So for corn, low yielding means 5 to 6 tons, but the average is 10, and the high values is 12. So it has to be one standard deviation lower than the mean of the field to be able to have constantly lower. If it fluctuates from +6 and then 1 year goes to 12, it's unstable. Understand the concept? So then we did the analysis, a very detailed mass balance and life cycle analysis, and we found all those impacts that you'll see in detail a little more here. So look at the percentage of each of the states. Those are the number we analyzed. Those are real numbers. Those are in hectares. So look at the state of Illinois has 6.5 million hectares of corn. Of the fields, we have 47% high and stable, only plus and minus 7. Look at the consistency across all the fields and all the state. So this is an automatic analysis that you know, hundreds of pages of codes to be able to get that, and then you got to 48. But they pretty much vary from, you know, 52, 40, 50. Sometimes Nebraska is higher because it's irrigated. It's much more stable. But anyway, and then you have 27, 25. The unstable zone is separated depending on the predominant aspect. So when you see in the case of Illinois, unstable is 23%, right? But it's 64% of the time it's high and stable, and 36% of the time it's low yielding. So I want to move faster. These are the rates, just I put it for you to see. The first number is what the farmers report. They say, how much fertilizer do you use? Many surveys. And they say, oh, we put 179. Other surveys, both with the agronomists and others, they really put 229. So there is quite a bit of discrepancy between the numbers. So we did the analysis and used in between. So you see the range, Indiana is 168 to 251. Since I know, because I talked to Ricardo, that is very different from Argentina, because you put so much less fertilizer. It's good to put less, but you put too little. The yield could be boosted. It's always on the extreme end. So this is the uptake and all the way to nitrogen use efficiency. So the low and stable zone that I was showing have a nitrogen use efficiency of 45%, which is really low. 55 kilograms are thrown away before you put, and only 45 are taken up by the plants. This is the results of the life cycle analysis, just to show this is only unused fertilizer. But the number there of 1.1 teragrams, it's pretty much what USGS has found in the Mississippi River in the Gulf of Mexico. So this is, the only difference is now we know where it comes from. And the CO2 emission and the amount they lose, about on average close to $600 million per year for fertilizer never used, with all the consequences from the environment. The other thing that we've been doing over the years is quantifying across all these fields. We have 3D, so you have areas that they are prone, vulnerable to be water deficit, and areas that they have water access by using a digital elevation model. So this is a work that I've done with my postdoc, Rafael Martinez Feria, who works for Pivot Bio now, and also Bernardo Maestrini, a previous work where we started doing this work together on the 3D analysis of fields. And if you look at the gaps, you can see seasonal rainfall. If you look at the areas in red, more prone to, as rainfall increases, right, the yield increases. But the blue areas, as rainfall increases, the yield decreases, because we have the opposite problem in the US, too much water, okay? So an analysis of observation of yields, basically in the same year, you could have 33% yield reduction on the deficit areas, and you can have about the same for water access, okay? So on average, at the same field, you could have 20% just due to topography, just by not having water available, running off. So now you see for each of the states, those are the percentage of areas. You can look at Illinois, then 3% depressions, so it's pretty flat, and hilltop 3%, and sloping very little compared to, so it's actually close to what you have here, really flat, but still undulating terrain. And so this is across the US Midwest. We have 2.7 million hectares that they are affected on the same year, both wet and dry. it's pretty interesting to see you have water standing on one side, and you have plants that they have less water and they're dry on the top of the hill. Okay, so the other thing we observed was the fact of most of the areas, the low-yielding area, this is not a center pivot. These are all the fields together. And you see, as you move away from the edges of the field, the high and stable tends to predominate, which is a combination of trees shading the edges, animals, compaction, drivers, and so that's also something that, but we have learned, we have learned where they are located across the Midwest. So this is only the low and stable zones across 80 million acres. And the total is 23 million acres of low productivity. And we know now how much is on the edges of the field and how many are in the middle of the field. Okay, so this separation. And the criteria is we calculated the pixels. When 5 pixels are combined together with low and stable, then they are basically adaptable to precision conservation. We don't want to have zigzag that the farmers, because they can be smaller areas. But so these areas are basically 1 acre, so half hectare. And you can see the fraction of the low and stable that they are on the field edge, and the rest are in the middle of the field. So the analysis from 35 million hectares that we analyzed, the total perimeters were 8 million, and the low and stable areas are 10 million hectares, and the one that they are on the edge are 3 million, and the rest are in the middle of the field out of the 10 million. We also did a detailed analysis. We know the cost of productions. So we like the word stability, right? Everything is stable, it's good, you can count on it. And so profit stability, it's not just the analysis on a single year as often, or either the previous year, but to do it over time. And so when you start integrating, for example, this first is the yield map 2016. So it goes from 170, which is about 12 tons, to 38 bushels, very little, 2 tons, 3 tons. This is the profit map for that year. This is the stability map for 11 years, and that's the profit stability map only for corn. So 7 years. And you'll see that the areas in red, in dark red, they lose $200 per hectare, because the cost of production in the US for seeds and everything, it's close to $700 per hectare fixed. And so they just don't make enough money. The break-even cost is 170 bushels. So you have to harvest 10 tons to be able to break even. This is subsidized. So the reason they keep doing that, because for $8 an acre, there is the insurance, the government of the insurance, and I also work a lot in developing countries, in poor countries. They can never be competitive when you have this level of subsidies. It's not good. So precision conservation is a recent paper that I published in Nature Food, and it's going from the profit stability map, profit stability, to decide which areas are variable rate. And you can use, the farmers doesn't have to do the second aspect of precision conservation. At least they have to realize that the areas of low productivity should not be fertilized in the same. So it could be as low as no fertilizer, or minimum amount, and then optimal, using different criteria, whether it's Ricardo's algorithm or his modeling, or we're very close to get much better delivery of nitrogen supplies. And so, but the problem is about being able to scale. And then you have increased biodiversity, where you just can plant pollinators and other plants on the side of the field. That's incentivized. Now, the positive things about this is that it's paid by the US government with this new initiative, 30 by 30, by allocating 30% of the land by 2030 in conservation. And so They can also sell carbon from offset because you have a perennial that does not require fertilizer, has deeper roots, and so you accumulate carbon. So this is a result of a recent paper that we just published in Environmental Research Letter of how much carbon you can basically sequester it using switchgrass, one of the grasses, the pollinators that can go on marginal lands across the different states. So just quickly, I go how we do prescription maps. So last year, we sent 5,000 acres to turnkey. So basically, final solution. We never knew these farmers. They get the prescription maps that goes into the applicator. So we combine, this is an example, we use the drones mainly to ask different questions, but it's satellite imagery, so any sorts of imagery. Modeling, you'll hear more about that, and the stability zones, that there's one level, additional level of separation, which is unstable depressions, if you have more tendency to have water accumulated, or you have unstable hilltop, which is dry. Okay, so these are the 4 layers that we use: stability map, digital elevation model, soil map, and water routing across the landscape. Where does water move and accumulates? So by doing that, we also integrate with SALUS. You can use any other model. SALUS is a model that is an evolution of the CIRIS model. It was developed by my former professor, Joe Ritchie, who CIRIS was actually started and funded by the US government to predict how much wheat was produced in Russia during the Cold War. So it was very strategic. So Joe Ritchie led that initiative, and CIRIS is still a good model, but does not have a lot of features that are in SALUS. And so together we built SALUS that is really sophisticated in soil carbon dynamics, and obviously running spatially. So that's an interest for people interested in learning about validation of models. That's a review that I wrote a few years ago where the models have been tested across the world. Those are all the different dots. This one point that I want to make to the modelers in the room is often crop models need to be validated beyond yield. So you need to check other variables. Sometimes you can get the yield right, but other things are not simulated correctly. So you have, this is an example of soil carbon that's, yield across, and again, variables in the soils or soil drainage. Just an example to show that you need to have additional data to be able to feel good about the soil-water balance. This is highly detailed field that we have with TDR at the long-term agroecological, and there is very little calibration you can do with the water balance. So it's either the model does well or does not well, and that's the roots and the depth. So one interesting point that I want to show you, this is the yield monitor on the top. You have stability map here, you can read on the left. Then you have the simulated yield map using the stability map. So if you parameterize the model with the criteria that we have, that you get a much closer reproduction of the yield map compared to if you only run the model by changing soil. So if you look at the soil, okay, the model captures that variability, but if you look at the corner where it said that it was blue, it is actually a good areas, but it was flooded. So in the years when it's done, the model will give you a high yielding because there is enough water. And so by parameterizing using the stability map, we have a better performance of reproducing yields across the Midwest, as you'll see in a minute. So this is an example of some of the prescription maps that we deliver. Those are some of the images. That's the prescription that goes into the nitrogen applicators. And that's just to show that for 67 fields in Michigan, what you gain is nitrogen use efficiency. So the yield is never affected or even gets bigger. So if you see the low and stable zones, the yield does not change. but with lower amount of nitrogen, you have a much greater nitrogen use efficiency, which means lower greenhouse gas emissions, means lower nitrate leaching. And so that's just a quick example. We use the model. This the original rate. The model runs on the updated rate using analogs of year, wet year, dry years, or average year, as you'll see. And that's the saving. So these are the types of weather. For each of the zones, where is the rate that basically you have very little response. And these zones, the model does quite well in reproducing what happens in the field. And so look at the low and stable, basically no response to additional nitrogen, not because it doesn't need it, just because it has no water to be able to take nitrogen out, using historical perspective. So for each of the zones, we know we run the model until yesterday's weather, and we have the ranges over the 30 years where it is compared to, and for the different zones. Anyway, I'm not going to go back. Climate benefits from reduced emissions. Look, if you look at the map, this is the latest work that I'm doing. You go from prescription maps, nitrogen applied, to how much nitrogen has been saved. So when you see where there is a 0, that means the plants needed the nitrogen, so you give the right amount, the top. But the map on the right, it's reduction of greenhouse gas emissions. So basically, the as applied map is a conversion that the farmers can upload to a system and be able to be certified to have reduction of greenhouse gas emissions. And this is at scale. If you use variable rate nitrogen for how much basically carbon credits, greenhouse gas emissions you reduce, and the credits and the cost at the current price of carbon per tons. And here is, if you do precision conservation, which means you basically do not put any fertilizer, it's even higher. One last example, and then I'll go towards the conclusion, is we recently published this work to improve prediction capacity. Forecast is critical for everybody, not just commodity traders, even for farmers to be able to know when to sell the the grains, where to store it, and so on. So again, in the last few years, I wrote this review where how much forecasting is done, which method is used. So you have for different countries, and the methods are, you can do a simple regression of historical weather variable, agrometeorology. You can use process-based, you can use remote sensing or survey. And that's the performance. So it's a really valuable paper if you're interested in doing forecasting. And the question here is, well, all of you pretty much here in Digital Ag use remote sensing. And I always bring this example. When you take an image, the sensor sees this green leaf, but after a point, the green leaves that the plants grow, the remote sensing still sees the same green leaf. And so the objective was, can we detect the impacts that is occurring between these stages when grain filling occurs? And by including quantification of water stress with a system approach, the system really meaning the interaction. You cannot use rainfall because it's just, you don't know how much is running off, how much is draining, just by using that data. So combining remote sensing with the crop model, you'll learn about that. So these are basically, we coupled again Landsat, all the different sources. We did this for 350 fields, and here is basically the field changing daily, and be able to capture all this through the integration with the crop model. That's the index, which is basically, it's a simple ratio between actual and potential calculated from the model. And so if the actual is equivalent to the potential, you have a higher number, right? You have 1. So when you see now the CDI, the greater the CDI, the lower the stress. And for the first time now, the forecast, we did it at field scale. And so if you look at A, B, C, D, A is the water stress across the field. Some were more uniform than others. B is the yield map measured for some of the field. C is the prediction only using vegetation indices. And then D is the vegetation indices plus the CDI, which is a much closer representation of the yield maps. And so, long story short, I didn't want to put the tables with improved regression, but some fields went from 0.3 R squared to 0.7 because they were highly affected by lack of water. And then we wanted to make this transferable, and so now any farmer can go on their own field and learn, even without running the model, where is the CDI depending on the type of year, the type of weather. So if this year has been, until the moment, has been a wet year, then there is the historical, for 30 years, there is the historical CDI ranges of value, depending on the probability that you want to use. And so it's a multiplier that you can get if you are on a wet year, dry year, or average year. And that still seems to work really well to transfer. So this map again, because I want to show how we do the prescription for precision conservation briefly. These are the fields that have joined this program. We received funding to give it to the farmers. So we received a large grant of for close to 4 million, but $2.5 million go to the farmers to do precision conservation. So that's the calculation, the procedure that we do. We put a threshold of what is the grain price, what is the fixed production cost. It will vary, but if we want to do across the whole Midwest, and then they received that map, which is basically they turn into the machine and they plant a different species, like a different seeding rate. And so this is for different fields. Some of the fields are significantly large areas where they lose money. And so that's the example of, again, linking profitability with the environment and be able to push towards a better management of the low productivity areas, especially in light of sequestering carbon, because these areas can make more money by selling carbon than selling low grains, because the yields are so low. And in the end, the last piece, that using the stability zones, talking to Telmo this morning, we sampled fields based on the stability zones, and it's pretty amazing how much basically behavior response you get from the low and stable zones. We have over 100 variables measured, including microbials and microbiological and enzymes on the stability zones, and we use this transect from central Michigan to Illinois, and these are for all the 240 points, the unstable zones and the high and stable zones, because remember, the high and stable zone, it's almost like the high and stable zones. It's just more variable. But the low and stable zone had the lowest amount of soil carbon constantly, because the lower amount of residue that is returned. The lab is moving into, instead of running one model, we run multi-model. So we have public databases, experimental, AppSim, EPIC, DaySand, Salus, and we train to run the model at scale very fast across the Midwest. We also have an ensemble of the machine learning algorithm, so you don't have to run the model every 3 meters, but you can run and train the model with artificial intelligence. This work was led by Rafael Martinez Ferias, and it's the same paper that I showed you in Environmental Research Letter. And so the models were validated for soil carbon, and then you can scale it across the entire Midwest. And that's an example. So this is running the switchgrass on low and stable zones for every subfield. And then the approach now is to push for planting cover crops on the high yielding zones to increase the amount of carbon that can be retained, because that's where the only sources is be able to add carbon and switchgrass switchgrass on the low stable zones, any of the perennials, and cover crops on the high and stable zones, which is really critical. This is an example to do subfield soil organic carbon with no tillage and cover crop. So how it changes over time. You see the years moving and how much carbon you gain. And that's basically some of the technology that I have developed and is being taken by this company that licensed the technology called SIBO Technologies that I've co-founded, and they distribute this information for free to the farmers as long as the farmers enroll into carbon programs. And so I wanted to conclude with some of the very quick analysis that SIBO does. This is an example of the low and stable zones and high and stable zones on soil health. This is a really compelling way of showing farmers where they are, current results, where they should have been, and how far can they go. What are the expected results? And the soil health, for the first time, it's separated into a fertility score and soil health score. Okay, so depends on climate, so it's a system approach. Then you see the values of low and stable and high and stable to be significantly different in terms of soil health. And so these are examples for different fields, just to give you. The farmers is basically realizing that there is a new crop, and this crop is called carbon. And so there is the difficulties in economic risk because they have to invest in money that they don't have. So a new project that the USDA is launching is to give subsidies to be able to push for that. One thing I wanted to show you is that one of the limitations of using bulk density, which is a critical variable to do the quantification. If bulk density is non-adjusted, you see with increases in bulk density, your sampling areas is significantly lower. So you need to, that's one of the greatest level of uncertainty, because the paradox is really here. If you see, you have areas where you start at 1.5 bulk density and goes to 1.3, and you have carbon that goes from 1.4 to 1.5. So you basically increasing carbon, but in the end, the stocks are less because you just have more porosity, and so you're sampling at different amounts. So if you don't adjust by soil depth, this becomes a problem. I wanted to share that with you. We can go to skip this. This is the example of the technology that the farmers can basically go on and see for every field. They can get the value of, you can click on any single field, you get the stability map, you get how much the piece of land is valued, what is the rental price, what is the predicted yield, and based on the stability map, and then you have a regenerative potential, which is basically what is the greenhouse gas emissions and nitrate leaching for every single field. So these are the technology that I have patented and they are using. The last point is, which is what I want to bring the consumers in. The consumers say, this is a story of what we're seeing now. The consumer says, I want to pay for regenerative ingredients. And then the food company says, outside, I need regenerative ingredients. Who can provide those regenerative ingredients? So they go, and SIBO tells basically by spying over the farmers and say, this is regenerative because it has cover crop and no tillage. This one is not regenerative. So the one with no regenerative does not receive the premium. The one with regenerative receives the premium, and the food company labels that as regenerative. And so there is a regenerative potential that is calculated for every single field with different potentials, and then it gets basically scaled up across all the areas, the Midwest, to show you how much potential is available there. There are basically $2 billion that farmers can make annually on selling carbon. This is a little bit too complex to do in a few minutes. I just wanted to show here this, you can read this in this paper in PNAS, where this is how agriculture was and how agriculture needs to be to become more circular. So again, sorry for that. We'll go. You can email me if you have a question on this. I'm going to stop here and back. I want to thank obviously the people in my lab and all the funders, and once again the organizer for inviting me to share this information. Thank you very much indeed.
Bueno, muchísimas gracias Bruno por la presentación, excelente. La verdad que siempre nos sorprenden tus presentaciones. Tenemos algún espacio para preguntas a la audiencia. Bruno va a estar durante el día y el día de mañana también con nosotros, para quienes por ahí hay poco tiempo para dedicarlo a las preguntas, pero es bueno, una oportunidad interesantísima para quienes están relacionados a esto. Nos ha mostrado muchos aspectos interesantes, como la agricultura de precisión también integra las cuestiones relacionadas al ambiente. Bueno, sin ir más, ¿alguno de la audiencia tiene interés en alguna aclaración, alguna pregunta? Allá al fondo. Me acerco con este micrófono, si querés, también Susana Alvarenque, compañera de INTA y estudiante de Bruno, nos puede ayudar en la interpretación.
¿Qué tal? Bueno, ¿en español?
Sí,
bueno.
Sí, no te preocupes.
Bueno, no, mi pregunta es cuán importante es la adopción por parte de los productores de esto que está pasando, está muy bueno.
I'll say in English. Okay. The producers, first of all, are surprised how much technology is evolving, and they're not aware of the profitability maps. They're not aware of yield stability maps at scale, you know, not just on their fields. In fact, they are surprised about, you know, learning. They are very intrigued by the possibility of using digital technologies to do variable rate, but at the same time, they are bombarded by different companies working close to them that they tell them different things. So one piece I really want to underline, the majority of the prescription maps in the US tend to put more fertilizer in the low productivity areas. And so the farmers are seeing this as something very different, and so which instead, if you don't look at nitrogen in the context of nitrogen and water, that those areas should receive a lower amount. And so they are overwhelmed, they're becoming educated, and they, unfortunately, they like to have turnkey solutions. So the final ultimate things, if you give them bits and pieces, they're just, you know, less active in adopting that technology. I don't know if I answered the question.
Acá, una pregunta. Cuando se genera algún tipo de, en los modelos para generar las prescripciones que comentabas, uno de los principales inputs son la estabilidad dentro del lote, ¿no? Cuando se genera algún tipo de cambio dentro del lote, ya sea una aplicación de yeso por elevado porcentaje de sodio, en esta zona, aplicación de algún fertilizante fosforado que pueda generar un cambio de potencial dentro del lote. El modelo que vos comentabas, ¿tiene algún grado de ajuste, algún modo de retroalimentar ese cambio que nosotros generamos dentro del lote?
È una pregunta muy linda. Il problema when you have a very dedicated management like lime, you put lime and you improve pH and you do that. If you don't inform the model that you have done, then the model can never capture the response, okay? But if you look at the yield maps the year after you have done the application, and it went from being low productivity to medium or to high, the zone has left the low and stable zone and became unstable. So any management that improves and moving the zones from low to high, the first step, they will become unstable because historically they were low yielding. Same thing happens in the US when you do tile drain. When you put a tile drain, before it was flooded, always low productivity, the plants did not emerge. They had differences in emergence, like what Susanna studies, and the yields were low. Then you tile drain, all of a sudden the yield is much more higher and stable. You need to inform the model. And so if you don't have that information, the only way to capture it is through remote sensing. And so the model alone does not tell you what to do. It's a combination of using the imagery with the models. And so the imagery can replace the farmer in case those information are not available. But you don't know why it's doing better. That's the problem.
¿Alguna otra pregunta en el auditorio? Bueno,
Acá.
Sí, Telmo.
Parabenizo por sua apresentação, Bruno. Impressionante. Onde estão chegando?
Grazie.
Se entendi bem, a eficiência de uso de nitrógeno e a disponibilidade de água à planta são dois indicadores muito importantes.
Sim.
Para maíz e trigo. E eu lhe pergunto para a soja. Nós outros plantamos muitos anos seguidos de soja e lo entendemos que o crédito de carbono de soja é neutro. Para a soja, quais seriam os indicadores claves? Graças.
Yes. Very good question, Telmo. Obviously, nitrogen is less of a problem. So you do require to put additional, either phosphorus or other, elements which have the dimension of spatial variability. But in the US, I have funding from the US soybean board. The main indicator is diseases. And so that's what they're interested in. And that's why I get funded, even though I'm not a pathologist, by using remote sensing and looking at, first of all, how early you can see them. So that's where we fly the drone, in addition to using planet imagery to scale, build those correlations. And the good thing is that we have a thermal camera, and we fly these aeroplanes with thermal imagery. Thermal is like the best indicators, because the plants will basically start not transpiring. It looks like that you have water stress, but it's a disease. And so the thermal temperature will be something that I would advise to do a thermal stability over time on soybean fields. It's basically you're going to see the disease will appear there much more, because it's a reflection of lower availability of water. The diseases tend to go in plants where they're less healthy to start with. And so by knowing areas that are more vulnerable, thermal will be the sensor to use. And then later you can run the model to see basically what is the yield reduction. You can't do anything about it, but at least you can predict how much lower yield you're going to get.
Bruno, thank you for your presentation. The question I have is, you talked at the end about regenerative agriculture, and you kind of equated no-till and cover crops as being kind of the biggest regenerative agriculture. But just as you mentioned, with tile drainage that improves the stability of yields and increases the yields, in much of the upper Midwest, with the wet conditions and things like that, typically no-till and cover crops actually can reduce yields substantially and also increase the variability. Can you talk a little bit about why you said that those two factors specifically improve or are giving kind of a positive thumbs up for regenerative agriculture?
Very, very good point. You're preaching to the choir. Yesterday we talked, Ricardo asked me, what is the percentage of no-till or cover crop? I think the technology is pushed towards this, but they're not the right reason for the Midwest, because, well, first of all, no-tillage is only 40% in the US, and cover crop, 5%. So the farmers know that that's not the most indicated way of managing regenerative. the government or in general sees the cover crop as the addition of carbon that you need to put through the roots. And so it's more about managing how long they stay when you desiccate them, and because at the same time they have the advantage of erosion protection, because the Midwest is losing basically a pound per bushel of corn that is produced. So soil erosion is still very important. But no tillage, you're very correct, that's not necessarily, it's too wet. So no tillage works well in good soils that have less availability of water because of the rainfall. So the solution there, the farmers are realizing that. The company kind of push for things that don't know as much. And I think it's the role of the scientists to identify what if through the either models or remote sensing. But you're dead right. The other thing is there are not even seeds available for cover crop to be able to scale. And so one of the options is to plant cover crops on low and stable zones, which they either have less water to produce the seeds. But it's how you manage the cover crop that hopefully will get a greater adoption. But the Midwest is projected to have even more rain than less rain. So it's a very hard nut to crack.
Bueno, agradecemos con un aplauso al doctor Bruno Basso. Va a acompañarnos durante la jornada y mañana, así que los invitamos a dialogar con él durante la estadía, que él quiera alguna cuestión adicional. Muchas gracias, Bruno.